So we're going to continue to talk about waves. And where we left off on this was this slide right here when we were talking about phase. And we were talking about how phase is a comparison between two places on a wavefront. And if the 2 points move in sync, it is in phase. And if they don't, it's out of phase. And sometimes it can even be perfectly out of phase. All right, well, we're going to continue on. And I want to talk now about the speed of a wave. Okay. Oh, but before I actually did that, I wanted to show you some examples. So I'm going to stop sharing for a moment. Okay. And I wanted to show you an example of a transverse wave. And so I'm going to take my camera and I'm going to take it to the back of the room here. All right. So about that far away, I guess. And what I have here is a spring. I have a spring that's fixed, that I tied to a bracket on the board. Okay, and this spring I'm going to have like this. Okay, and if there were no gravity, it would be horizontal. And if I generate a wave like this, look how the coils of the spring vibrate. You know? They vibrate up and down. Okay? Each individual coil would vibrate up and down. All right? And so this would be an example of a transverse wave, a wave which the particles in the medium vibrate perpendicular to the direction of wave travel. Okay? That would be an example of a transverse wave. Okay? Now, I want to show you an example of a longitudinal wave. Maybe not that far. Okay. You see my desktop, and I have it's like a long slinky, and I'm going to attach this. I'm going to anchor it to the tabletop with an inactive gas jet. And then I'm going to do this. I'm going to vibrate it back and forth. And you can see the compressions travel on down the spring. And if I focused on one individual coil of the slinky, it would vibrate to the right and to the left and as the wave moves parallel to the vibration of the coils. Okay? This is sometimes called a compressional wave, okay? And I think you can see why, because it has compressions. And it also has rarefactions, where the coils are spread apart. Okay, so those are visual examples of transverse and longitudinal waves. Okay, and I wanted to show you that. So you could see it. All right, now, while I have it like this, I want to talk about the speed of a wave, what affects the speed that waves travel down a spring. I'm going to use this as an example. Okay. Now, I really wish this were kind of horizontal, but it isn't. So I just like to get an eyeball, just kind of get an eyeball of the speed that these waves are traveling down this spring. Okay. Now, if I have a short wave, a small amplitude wave, like that, watch the speed that it travels down. And now I'm going to create a large amplitude wave. Now, that second wave was at least 5 times the amplitude of the first one. Okay, there's the amplitude there. There's the amplitude there. Does the speed change for the tall ones or for the short ones? I would say no. Okay? I would say the small amplitude waves and the large amplitude waves travel at the same speed. Okay? So amplitude of the wave does not affect the speed of travel. Okay? Now, what about the length of the wave? If I vibrate my hand up and down very quickly, I create small wavelength waves. And I'm just going to just create a 1 or 2, and you can see how the speed with which they travel. Okay. That's a short wavelength wave, is about that long. Now, a very long wavelength wave would be like this. And that wavelength is really long compared to the first. And I think you'll agree that, let me settle this thing down a little bit. If I create, he travels that fast. If I treat long wavelength wave, it travels again at the same speed. So the wavelength of the wave also does not affect the speed. In fact, whatever type of wave it is, does not affect the speed with which it travels through the spring. What does affect the speed is the spring. I'm going to change this spring by pulling it in of the waves. Okay? All right? Now, there's a lot more tension in the spring. Okay? And now, I think you'll agree, the speed is a lot different. Okay? The speed is a lot different. So it's not the wave that determines the speed. It's the material, it's the medium, it's the thing that's traveling through that determines the speed. Okay? All right? Okay. Let's write some stuff down. Write some stuff down. Okay. All right. So let's get back to my presentation here. The speed of a wave does not depend on amplitude or wavelength. Okay. All right. It depends only on the material the wave is passing through, the medium of travel. Okay. And what's an example of a medium? Well, a spring, the spring, or water, or air, or rock, or anything that the wave can travel through. What do you mean? Waves can travel through rock? Yeah, they can. We'll talk about that later. All right, so a medium is what the wave is traveling through. Even if the vacuum of space is a medium. Okay. Okay, now let's talk about the depth of water. Let's even the depth of water. If I change depths of water, that's a different medium, because waves can travel through water more easily in certain depths of water. And I want to ask you, and it has to do with how easily the wave can get through the water. So I'm going to ask you, in which depth, if you had to guess, in which depth can waves travel more easily? Deep water or shallow water? In which do they have more freedom of movement? Deep water or shallow water? What do you think? What do you think? Think about that for a minute. Okay, waves can travel at different speeds in deep water or shallow water. No guesses? Well, as it turns out, the deeper the water, the more easily the wave can pass through it, because there's less in the way, right? So as it turns out, the speed in deep water is different than in shallow water. It's faster, okay? It's faster. And as the waves approach the shore, they slow down and they fall over. They fall over. The bottom of the wave runs into the ground as the ground is rising to the shore, and they fall over. This would be the same thing as if you were running blindfolded across a field, and if you're running with your eyes closed across a field, and then you hit an upslope, like the ground would be going up like a hill. Well, your feet would hit the hill, and the top of your body would still be moving, and you'd face plant, right? Well, the wave is kind of doing the same thing. The bottom of the wave hits the ground as the ground is rising. The top of the wave is still moving forward due to its own inertia, and so the waves fall. Okay, and that's where you get the curl of a wave, and we say the waves break. Okay, so anyway, the speed of a wave depends on the medium, and within that medium, it's a constant. Okay, so for deep water, large amplitude waves, small amplitude waves, short wavelengths, long wavelengths, for a particular depth of water, the speed is constant. If it goes into shallow water, it's a different constant, but it's still a constant no matter what the wave is. Okay? And that is, so it does not depend on the wave. It depends on the medium. And there's an equation for this, and it looks like this. V is equal to F lambda. V is equal to F lambda. Where? V is equal to the speed, F is equal to the frequency, and lambda is equal to the wavelength. Okay? Now, this equation is good for all types of waves. Okay, I'm going to repeat that. This equation is good for all waves. If there are waves in a spring, or if there are waves in water, or if there are sound waves traveling through the air, or even if there are light rays traveling through the vacuum of space, they are governed by this equation. This should go in your equation bank and take a prominent place, because we're going to come back to this a number of times when we talk about water waves, when we talk about sound waves, when we talk about light waves. We're going to come back to this equation. Okay, this is an important. Yeah, go ahead.
When I was doing my own research last night, I found an equation that was the same exact thing, but the F was a C.
Yeah, okay, that C represents light. That C is the speed of light, and that's only for light waves. And I'll bring that up when we get there. Okay, Johnny?
Okay, thank you.
All right, but yeah, that's C. C in physics is a very, very special thing. And we'll talk about that when we talk about light. But you're right, yes. So it said C is equal to F lambda, right?
Yes.
Yes, because C is the speed of light. All right, thank you for pointing that out. Now, let's do an example. Let's do this. If a wave of frequency 2 hertz is traveling in water and has a wavelength of 0.75 meters, with what speed is the wave moving? All right, I'm going to unshare because I want to do this. I want to do this in class. I want to do this on the board myself. So I want to do this. So I'm going to zoom in a little bit. All right. Okay. Now, so what we have is frequency, which is 2 hertz, and the wavelength is 0.75 meters. What we want to know is what is the speed. All right. Okay, we're going to use V is equal to F lambda. All right. 2 hertz times 0.75 meters. 0.75 meters. Okay, now, numerically, 2 times 0.75, that's equal to 1.5. Okay, now, what about the unit? We have a hertz times a meter. Okay, now, a hertz, if you recall, a hertz, I defined a hertz to be a wave per second. A wave per second, okay? But it could be something else. If it were a pendulum that's oscillating back and forth, it would be a cycle per second. If it were the moon orbiting the Earth, it would be an orbit per second. So the numerator can be different things. And actually, the numerator does not have a dimension, okay? Dimensions for purposes of canceling out units, a hertz is just a 1/2. Okay, so just for the purpose of canceling out units and stuff, a hertz is a 1/2. Okay, and then if I multiply that 1/2 times a meter, what we get is meters per second, and that would be the speed. Okay, all right. So it's a fairly straightforward equation to use. We're going to use it many times as we go through this unit. All right. All right. Okay. Let's see. What's next? So I'm going to share again. And through that. Yep, did that. Quiz time. All right, quick quiz. Don't worry, I'm not going to grade you on it, but I am going to ask you. Given the following, okay? Given the following, what is the wavelength of this wave? Is it 0.5 meters? Is it 1.2 meters? Is it 1.5 meters? Or is it 2.4 meters? Now, if you were in my room, and I wish you were, I'd have you hold up fingers. But I can't do that. So instead, let's see. And I can't even get gallery view, and I'm recording, so I can't change my real computer to gallery. So I'm going to ask you for the chat window. Chat window. Which choice? 1, 2, 3, or 4? What do you think? What is the wavelength of this wave? 4 is a very popular response. Well, you're right. Yay! It's the crest to crest distance, 2.4 meters. Yeah, crest to crest distance. That's wavelength. Okay, next one. What is the frequency of this wave? Is it 1.5 hertz? Is it 2.4 hertz? Is it 10 hertz? Or is it 15 hertz? What do you think? Chat window, which response? Which choice is best? Which choice is best? Choice 1, choice 2, choice 3, or choice 4? What do you think? What do you think? Not a lot of guesses for this one. Maybe you're a little unsure. Well, frequency. Okay, frequency. Remember what frequency is? Frequency is waves per second. 15 waves in 10 seconds corresponds to 1.5 waves per second. And that's choice 1. Yes, choice 1. All right. Next one. What is the period of this wave? What is the period of this wave? Oh, gee, Ms. Dodge, I don't remember what period is. Well, look back in your notes. What is period? How would I define period? And how would it pertain to this wave? Oh, by the way, I forgot to give you your choices. Sorry. 1.5 seconds, 1.0 seconds, 0.67 seconds, or 0.5 seconds. What's the period of this wave? I don't remember what period is. Period is the amount of time per wave, the seconds per wave, which is the reciprocal of the frequency. Okay, the reciprocal of the frequency. Yeah. So it's 1 over 1.5 or 0.67 seconds. Choice 3. Yeah. Choice 3. Choice 3. All right, next one. What is the amplitude of this wave? Is it 2.4 meters? Is it 1.2 meters? Is it 1.0 meters? Or is it 0.5 meters? What is the amplitude of this wave? What's the amplitude? 4 is a very popular answer. And that's a good thing because you're right. Yeah, amplitude is the distance from the equilibrium position to a crest, or from the equilibrium position to a trough. Yes. Yes. Choice 4. All right, last one. What is the speed of this wave? Is it 0.75 meters per second? Is it 3.6 meters per second? Is it 1.6 meters per second? Or is it 1.8 meters per second? Which choice is correct? What is the speed of this wave? What is the speed of this wave? We did a problem like that just a moment ago, just a few moments ago, where we determined the speed, right? Remember what speed was? Speed was V equals F lambda. And we knew the frequency, 1.5 hertz. We knew the wavelength, 2.4 meters. And after we multiply those two, we get 3.6 meters per second. Choice 2. Yeah, choice 2. Okay. All right. So a little quick quiz about stuff that we've done so far. Questions, comments? Okay. Then I want to talk about the energy of a wave. Okay. Now to do that, I have another demonstration. So I'm going to stop sharing. And for this is going to be a little bit difficult for you to see because I can't project it against the board. And the reason why is I don't want to endanger that speaker. So I'm going to do this over here. And I hope that I hope you can see it. I don't know how well you can see this, but I'm just going to try it. Okay. Actually, I think I might have to zoom out a little bit farther. Hold on a second. Move these books to a different desk. Okay. So, yeah. All right. So anyway, I have this spring tied to a bracket on the wall, and I want to transmit energy. And I want to transmit energy to the bracket. Okay. I want to transmit energy to the bracket. Now I could do that by simply letting the spring go. And then it would compress up and crash into the board. Okay, that would be delivering energy via a collision. I don't want to do that. I want to do it by a wave instead. So I want to deliver energy to that bracket. Now I would like to deliver enough energy to rip that bracket right off the wall, or to break the string that I have tied. Now, am I going to do that with a short wavelength wave? Okay. Or a long wavelength wave? No, that doesn't seem to be delivering a whole lot of energy. Okay. So by changing the frequency, okay, that's not going to do it. What is going to do it is the amplitude of the wave. Okay, larger, 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 larger. Okay, large amplitude wave is a lot more likely to rip that bracket right off the wall. Okay, a little wimpy old short one won't. Okay, so moral of the story: the energy of a wave does not depend on its wavelength, does not depend on its frequency. It depends on its amplitude. Okay, that's why I didn't want to take a chance on ripping that speaker right off the wall. So hopefully you can see this. Okay, all right, enough to see. Okay. All right. So, getting back to that slideshow then, the energy of a wave, now I have to qualify this. The energy of a mechanical wave depends on its amplitude. Okay, what do you mean by mechanical wave? I'll go over that later. Okay, the energy of a mechanical wave depends on its amplitude. Okay, low amplitude, low energy. And this is what we see in no wake zones. In no wake zones. Now, where do we see no wake zones? What would happen to the speaker? I might rip it right off the wall or damage it somehow. And I don't want to do that. So that's why I did that like I did. Now, no wake zones. Where do we see no wake zones? Where do you see those things? They're in water. The wake is the waves created by a boat going through the water. Where do you see no wake zones? Anybody know? No? Never heard of those before? Well, no wake zones are zones where you want the waves to not have a lot of energy. For example, if there's a swimming area in like a state park for a lake, okay, and your 4-year-old daughter is playing in the water in like waist deep water, okay, like I don't know, 8 feet off the shoreline or something like that, or maybe 6 feet off the shoreline, and if there's this speedboat went past like at 60 miles an hour, 30 yards away, it would create this huge waves that would they would create these huge waves that would inundate the kid, blast the kid into the shore. You could hurt someone. So they have these around swimming areas. to prevent large energy waves from hurting small children and people, right? Another place they have these is around piers that have boats docked up to them. So the large amplitude waves don't crash the boats into the docks and damage them, right? And you see these also in channels between bodies of water. You know, I come from Wisconsin, right? Now, it's right next to Minnesota. Minnesota has 10,000 lakes, right? Land at 10,000 lakes. Wisconsin has 14,000 lakes, right? So there's just a lot of lakes. There's lakes everywhere. And if you go up north, they have what's called a chain of lakes. They're just a string of lakes that are more or less in a straight line, made by the glaciers. Okay, what they did was they cut channels between them so that you could go from lake to lake to lake in your boat, right? And these channels are about, I don't know, 40 meters wide, something like that. And they're lined with cottages that cost like $500,000, all right? And with piers and docks and things like that, all right? I could never afford to buy one of those cottages. Well, if you have a speedboat that goes from one to another at like 60 miles an hour, it's going to create these huge waves that bash their boats against the pier and erode their shore away. You know, their lawn would get smaller over time, which isn't good, right? So they have no wake zones in the channels between these, okay? So they're a place where you want to create, where you don't want to create large energy waves, okay? So you slow the boats down. The speed limit, 15 miles an hour, something like that. All right, that's a no wake zone. And because we want low energy waves, right? So their purpose is, among other things, to prevent shore erosion and prevent damage to your boats. Okay. All right. Counterpart: high amplitude, high energy. All right. There's a surfer in there. I don't know if you can see him. This is a very high amplitude, high energy wave. If this person isn't super careful or very good at surfing, they could get killed, actually, because this wave could drive this person into the bottom where all the rocks are, you know, break his neck or whatever. So this is very dangerous, okay? Very dangerous wave. You got to know what you're doing to get on one of these. Okay, it's a very high amplitude, high energy wave, okay? Another example of one is a tsunami. A tsunami, now they used to call these tidal waves, but they're not caused by tides. They're caused by undersea earthquakes or volcanic eruptions. And under the right conditions, they can create an incredibly large amplitude wave, okay? And these can travel through the ocean and land on the shore where all the people are, okay? Now, here's an example of one that hit the island, the Thai island of Phuket in 2004. Look at the height of this wave, okay, compared to the buildings. This wave, this tsunami crashed onto the shore and killed thousands of people. It's such an incredibly high energy wave. Now, some people were really stupid. They said, oh, tsunami's coming, huh? I got an idea. Let's have a tsunami party. Let's go watch it come in. So they went down to the shore and they had, you know, the guys, you know, taking pictures and whatnot. Bad idea. 30 seconds later, they're running for their lives. Some of them didn't make it. So tsunamis are incredibly dangerous things, okay? Funny part about a tsunami, though, if you are out in the open ocean, you might think, well, now if you're a boat out in the ocean and a tsunami is going to come, it's going to just capsize you and stuff like that, right? Well, no, not necessarily. The tsunami might pass right underneath you, and you wouldn't even know it. Right underneath your boat. It's not like it takes the boat. Here's my mouth. Now it's going to go, whoa, and crashes in it. No, it might pass right underneath you because the vast majority, although it's an incredibly high amplitude, high energy wave, the vast majority of it is below the surface, okay? And it can travel through deep ocean water at hundreds of miles an hour and with very, very little energy loss, okay? Because there's nothing to stop it. It's just deep ocean water. So this tsunami, the one in 2004, it killed thousands in Thailand, and it went all the way across the Indian Ocean and crashed into the shore of India. and killed a couple of hundred people there. It traveled 2,000 miles at, I don't know, 150, 200 miles an hour. And it killed a couple hundred people in India. So it contained all that energy. It didn't lose any energy, right? So these are damaging things, right? Now, but again, if you're out in the open ocean, you might not even know they're there. But what happens, because they're most of it's underwater, but what happens when it gets to the shore? Well, analogy. Let's say you're out at the lake and you're cooking burgers on the shore while your friends are swimming. And let's say Bill, your friend Bill, is out in water and he's in pretty deep water. The only thing you see is his head. And he's in neck deep water. All you see is his head, right? And then so you're cooking the burgers and you say, "Hey, Bill, burgers are done." And Bill says, "I'll be right there." And you start watching Bill as he walks out of the water, right? And at first all you see is his head. And then as he walks out of the water, then you see his shoulders, and then you see his chest, and then you see his tummy, and then you see his swimming suit as he climbs up out of the water. Well, guess what? A tsunami does the same thing. Let's say that this is a deep ocean water, and then here's the shore. And the water is this deep normally, right? You have a boat you have a boat in the water, okay? Your yacht is in the water. Now, tsunami occurs. Now, the vast majority of that wave is below the surface. Super high amplitude, but most of it's below the surface, right? You might not distinguish it from all the other waves that are on the ocean. But what happens when it gets to the shore? Well, same thing that happened to Bill. It starts climbing out of the water, okay? Then it does the same thing that all waves do. They hit the bottom, they get in the way, and they break, right? Just like you did. You'd run into this hill blindfolded. And this wave keeps crashing onto the shore and delivering immense force on the shoreline, where all the villages are, where all the resorts are, right? And so tsunami they don't happen often, but when they do, they are devastating. They are devastating events. Okay? That lush tropical paradise that was Thailand, inundated by salt water, killed all the vegetation. Okay. All right. So these are incredibly devastating events, right? They don't happen often, but when they do, they're devastating. Okay. Now, since moving to the West Coast, I've been to San Diego, I've been to San Francisco, I've been to Seattle, and they have tsunami evacuation routes, right? And if you're near the shore, when one of these are coming in, get away from the shore. If you're on the water already, get to deeper water, as deep as you can get, because these are bad things. Okay. Okay. All right. Next topic, reflection from a boundary. Now, on Wednesday, I had you guys watch a video, and in my wave tank, I bounced water waves off of straight boundaries and curved boundaries and stuff like that. This is going to be a little bit different than that, okay? There are two basic types of reflections that I'm going to talk about, all right? And the two kinds are one's called a fixed end, and the other is called a free end, all right? Now I'm going to stop sharing because I want to do this on the board. Okay. Zoom in a little bit. Now, first thing I'm going to do, come on, a little bit. I want to do a fixed end reflection. Okay? And what do I mean by fixed end? I mean a wall. So it's like I have this spring that's connected to the wall. Okay. What I'm going to do is I'm going to send a pulse into this wall. Okay. And this wall, which I will draw like this, qualifies as a fixed end. Okay. The end is fixed to the wall. Now, just talking about the spring itself, what the pulse wants to do is pull the coils of the spring up. So as this pulse travels down the spring, it pulls the coils up, okay? Until it gets to the back end, it pulls it down. Just talk about the front end, it wants to pull it up. But then it gets to the wall, and it tries to pull the wall up. But it can't, because it's a wall, right? It's fixed. So instead of the pulse pulling the wall up, the wall pulls the pulse down instead. All right, and the reflection of this, when it goes back to the left, will actually be on the other side. It'll be on the downward side of the equilibrium position, okay? And we call this an out of phase reflection. Out of phase reflection. Out of phase reflection, okay? All right. Now, I have a simulation that will show that in a moment. Actually, maybe I'll do that. Maybe I'll do that now. So let me share the screen once again. And we can see that here. As a pulse goes into the wall, okay, it gets over to the wall, and this fixed end, and it tries to pull this fixed end up, but it can't, right? Instead, the fixed end pulls it down. So this would be an out of phase reflection, okay? Goes in on the top side, comes back on the bottom side, okay? Okay, now the counterpart to that is something called a free end, okay? And here's how we're going to accomplish this. I'm going to send a pulse along a spring, and at the end of the spring is a ring that's around a pole, okay? And this ring is free to move, okay? So this would qualify as a free end. This will qualify as a free end. Oh dear. Okay. All right, now, when this pulse is traveling, it's pulling up adjacent coils, pulling up adjacent coils, pulling it up until it gets to the end. Now this ring, since it's free to move, it can go up, okay? And when it goes up, it comes right back down because the back end wants to pull it down, right? Front wants to pull it up, back end wants to pull it down. So it gets pulled up and then pulled down. But when it does that, it comes back on the same side. Comes back on the same side. So this reflection is in phase. This is an in phase reflection. All right? Okay. And this would be showing you that, I'll give you a moment to copy that stuff down, okay? Let me zoom in a little bit so you can see it a little bit easier. All right. Oops, wrong way. All right. Okay, and then, by the way, I'm recording this, so I'm going to try to load this. And then once I share the screen, we get the simulation of this. Whereas this was the fixed end reflection, okay, now we can have a free end reflection. When the end is free, and you can see it pop up and then pop back down as the back pulse gets there, and it comes back on the same side, and we would call that an in-phase reflection. Okay? Now, why am I going over this? Well, this plays a very big role in the production of music. Okay, very big role in the production of music. And since music is pretty important, at least to a lot of us, then this is kind of a big deal. Okay, so all these general things are going to lead up to some applications. All right, stop sharing. Okay, actually, I think I'll have you write down one more thing. Before, and that's something called, what's next is something called the superposition principle. just write that down, and then I'll give you an example of it. Okay. Superposition principle. All right, now, let's say that you guys were, okay, stop sharing. Let's say that you guys were actually in here, as I wish you were, and we were having class, and it's work time, so people are in small groups working on homework or whatever, okay, and I'm helping out students, and I'm on one side of the room with my kind of back turned to the rest and helping out a student, and then somebody behind me, like on the other side of the room, asks, "Hey, Mr. T, could you come over here when you get a chance? I have a question." Okay. Now, let's say that was Bill, all right, my student Bill, and now if now the sound wave that Bill generates travels through all the other sound waves that are being generated by the people that are chit-chatting away between us, okay? But I would still be able to understand what he says. Now, think of when you've been in a crowded room, like, I don't know, around in the quad during lunch, and your friend from across the way calls your name. You can hear that. Assuming you can hear it, you can understand it. You might even, since you're looking down, scooping your soup or whatever, you might even recognize their voice and say, "Oh, that's my friend. That's my friend." Or I would recognize Bill. "Oh, Bill has a question." I would recognize their voice, even though it's passing through all the individual waves in between. So part of it would be as if, talking about just my Bill example, as if Bill were the only person in the room. Forget about all the other people chit-chatting away. The sound wave that he generates retains its own identity. Not only could I understand the English, because it doesn't get garbled up by the stuff it's passing through, not only could I understand the English, I might even recognize that it's Bill. Okay? So each wave that's generated retains its own identity. Okay? Now, of course, if everybody's talking in here, it's going to be loud because all the sound waves all the volume is going to add itself up, right? Well, that's what the superposition principle is. Okay? The first part of it is this. When two or more waves are traveling in the same medium, each wave proceeds as if there were no other waves present. So Bill's voice is going to proceed through all the other sound waves, but retains its own identity. Another example. If I went out to my car, or if I'm listening to the radio on the way home, as I do sometimes, how many different radio stations could I pick up in my car? 20? 30? 40? AM and FM? So even though all those other radio waves, all those waves are traveling through the same air, I can focus in on one. And it is as if it's the only radio station in the entire world. Okay? So each wave proceeds as if there were no other waves present. But if everybody's talking, it's going to be loud. It's because the resultant displacement of the particles in the medium is the algebraic sum of the displacements from each individual wave. If I'm agitating the air, and Bill's agitating the air, and Sue is agitating the air, and Billie Jean is agitating the air, all those agitations are going to add up. Okay? All right? This is the superposition principle. And I'm going to present it using these pulses down here as an example. All right? I'll give you a moment to write that stuff down. A lot of words there, I get it. Okay. If you don't get this, remember, this is in multiple forms in the Schoology page. All right, so you can get this later. All right, let's take a look at these two pulses as they travel towards one another. Okay, they're going to travel towards one another like this, and then they're going to start overlapping. Okay, now I'm going to talk about this. Let me go previous a little bit. I'm going to talk about these pulses in terms of thirds: the left third, the middle third, the right third, stuff like that. Okay, check out what happens when they start to overlap. All right. Now they're overlapping right here. The pulse on the left, the right-hand third wants to take the spring up 1 unit. The left part of the right-hand pulse also wants to take it up 1 unit. Well, if this pulse wants to take it up 1 and this pulse wants to take it up 1, the overall effect is to take it up 2. And here's what the spring would look like at that moment. We do not see the individual pulses. We only see their superposition. Okay? Let's go 1 unit of time later when they're completely overlapped. What does the spring look like now? Well, the left-hand third of this pulse wants to take it up 1. The left-hand third of this pulse wants to take it up 1. +1 and +1 is going to be +2. What about the middle? The middle part wants to take it up 2. The middle third wants to take it up 1. +2, +1, +3. What about the right-hand third? +1, +2, +1, +2, +3. So at this moment in time, the spring would look like this. All right. All right, moment of time later. Now they're beginning to emerge from one another. The only place they're interfering is right here. And the back side of this pulse wants to take it up 1. The back side of this pulse wants to take it up 2. So the overall effect is +3. Okay. And then they emerge from one another and continue on their way. Okay? Now, so the pulses would travel through each other, right? And emerge from each other unchanged. They had the same shape coming out as they did going in. The characteristics of each pulse do not change. Okay? But where they interfere, the medium changes. Okay? And while they're interfering, we do not see their individual pulses. We only see their superposition. So here's what we would see if we took a video of this and looked at it frame by frame. Here's what we would see. Okay. All right. Okay. This kind of interference, when they build each other up, is called constructive interference. Constructive interference. Constructive interference, right? All right, constructive interference. Okay. I used to watch this show on the Discovery Channel called Deadliest Catch. Did you ever hear of it? You hear Deadliest Catch? It's on Discovery Channel. Okay, and it's about crab fishermen off the coast of Alaska, right? And crab fishing is supposed to be like the most dangerous job in the world, so they made this TV show about it. And it's kind of compelling in its own right, so I watched it for a while. And they talked in one episode about another ship that got capsized by what they called a rogue wave. A rogue wave. Okay? And it was this wave that wasn't produced by a storm, wasn't produced by, it just appeared out of nowhere, this huge wave that capsized a ship, right? So I was wondering, what would produce such a thing? And I got to thinking, there's many, many waves that are traveling through the ocean at the same time. so let's say there's 15 waves all traveling through the ocean at the same time. What would happen if all those waves at a particular point just happened to be at a crest, so that all 15 of those waves wanted to pull the water up? Well, all those ups, those individual ups, would add up to give a huge resultant up. And so just at that particular location, at that particular time, all those waves constructively interfered and made this huge wave. And if a ship was at that location at that time, just by terribly bad luck, it might be enough to capsize the ship. Okay. So I was thinking, I never actually researched it, but I was thinking that might be the cause of one of those waves. Okay. All right. If anybody wants to look that up and send me the link, I'll throw a bonus point or two at you. If you do the research for me. All right. What causes these? But that's my idea about what does. The constructive interference, just by dumb luck, dumb bad luck, to all happen, to all converge at the same point at the same time. Okay. All right. Now, finally, let's talk about pulses that are on. Oh, yeah. And if you were here, I'd have this worksheet that could do, but I couldn't figure out a way to get this to you easily, so never mind. Now, let's talk about where one pulse is on the top side and another pulse is on the bottom side. What's going to happen now? Well, let's see. As they begin to overlap and interfere, what is the spring going to look like? Well, this is the place where they're interfering. The left-hand pulse wants to take it up one. The right-hand pulse wants to take it down one. Positive one, negative one, they're going to cancel each other out. Okay, this is called destructive interference. Let's go forward one moment in time where they're completely overlapped. What does it look like now? Make a prediction. What about this third? What about this third? What about this third? What's it going to look like? Okay. Well, it's going to look like this. Oops. Oh dear, went the wrong way. Here, okay, it's going to look like this. Look down below. The left-hand third cancels itself out. +1, -1. The middle third, +2, -1, +1. The right third, +1, -2, -1. Okay, that's what it looks like when it's completely overlapped. As they begin to emerge from one another, what does it look like? The only place you're interfering is right here. +1, -2, -1. And then they emerge from each other like this. Okay. Now, we do not see the individual pulses when they overlap, but they do emerge unchanged, the same as when they went in. All right. They retain their own characteristics, but where they superpose, where they interfere, we see this. Okay. And that's the superposition principle. All right. Okay, now, number 9, I believe it is on your waves worksheet 1, asks you to draw the superposition of these. Okay, I'd like you to do that. The next topic is, oh yeah, and we would do something like that if you were here. The next topic is something called standing waves, which are super important, again, in the production of music. All these things, among other things, but one of the most applicable, one of the most widespread applications of the stuff we've been talking about in the last day plus is music. Okay. And so I'm going to address that. And since that's so important to a lot of people, in fact, more people at this school than other schools, okay, music is a big part of this school. I want to spend a little time talking about that. All right. So But that's it for today. Now, you can now complete Waves Worksheet 1, or what I called Don't Make Waves. I would like you to complete that and submit it to Schoology by the end of the day, Sunday. Okay? And then I'm going to give you homework points for completing that. Okay? Doesn't have to be right, but I do want to see some answers. Okay? And then we'll go over the answers to that next time we meet. The other worksheet that I had, Waves Worksheet 2, which I also called A Day at the Beach, the one from the video on Wednesday, you cannot finish that because there's another video that you need to watch to complete that. Okay, so Waves Worksheet 2, or what's called A Day at the Beach, you can wait with that. But Don't Make Waves, which is also Waves Worksheet 1, is due by the end of the day Sunday. And I'm going to give you the last 10 minutes of class to work on that now. Okay?